next or the second lesson on unit BCH 1108. This is Organic Chemistry 1, and my name is Peter Karuri. Now, in this, we are now going to specific group groups of organic compounds, and we'll start by looking at alkanes. And before we look at alkanes, we have to define the group in which, or the general extent of compounds in which it belongs, and that is the in a group of compounds referred to as hydrocarbons. Now, hydrocarbons generally, organic compounds per se are divided into different series depending on the nature of the functional area, or what we call a functional group. And those series in which we divide organic compounds are what are referred to as homologous series. Now, within the homologous series, we have a series of three distinct groups that is referred to as a series of hydrocarbons, which consists of alkanes, alkenes, and alkynes. So I'll start by defining the word hydrocarbon. Now, hydrocarbons are those organic compounds where we have only two elements in the compound, that is carbon and hydrogen. So generally, the term hydrocarbon refers to compounds that only have carbon and hydrogen as the elemental component. Now, within hydrocarbons, we can divide the hydrocarbons into two main classes, or into two main areas. That is what are referred to as aliphatic hydrocarbons and what are referred to as aromatic hydrocarbons. Now, we will not go to the area of aromatic hydrocarbons, which is a chemistry on its own. We shall basically in this area deal with aliphatic hydrocarbons. Now, but to define is that the difference between aliphatic and aromatic hydrocarbons is that whereas aliphatic hydrocarbons can exist either in chain forms, that is no rings, aromatic hydrocarbons only exist in ring forms. And the difference between aromatic rings and aliphatic rings is that aromatic rings have delocalized electrons, electrons that are able to move freely throughout the ring. So in a case, I'm saying we are looking at aliphatic hydrocarbons, and we are going to look at alkanes in this case. Of course, the other aliphatic hydrocarbons are alkenes and alkynes. So this is generally what I was saying, that hydrocarbons are divided either into aliphatic or aromatic, and within the aliphatic hydrocarbons we have alkanes, alkenes, alkynes, and generally cyclic aliphatics, which can either be alkanes, alkenes, or alkynes. Now, so the main topic is about alkanes. Now, alkanes are what are referred to as saturated hydrocarbons. And the general molecular formula for alkanes, that is non-cyclic alkanes, is CnH2n plus 2. This is a formula, meaning that for every n number of carbons, you have 2n plus 2 number of hydrogens. However, in their cyclic form, alkanes generally have the formula CnH2n, meaning 2 less hydrogens compared to in non-cyclic alkanes, meaning that if you have n carbons, then you have 2n hydrogens in cyclic alkanes, where n is an integer, meaning 1, 2, 3. So we are going to look at this homologous series of alkanes. Now, we will start by looking at the homologous series of straight chain alkanes. And they start with the lowest number of carbons going to higher number of carbons. And we are going to look at straight chain alkanes. Straight chain alkanes means that you have no branches. That is, every carbon is only bonded to the next carbon and no side carbon. And the simplest is one with one carbon. You have, which is referred to as methane, 2 carbons, ethane, 3 carbons, propane, 4 carbons, butane, 6 carbon, hexane, and 7 carbons, heptane. Now, the general formula gives you the number of carbons and the number of hydrogens. And because in this case, we are saying that there's no branching, each carbon is bonded to the next carbon, and the structure, we draw, when we are giving the molecular structure, we show that we have continuous carbon atoms, and this is the way to represent those molecular structures. If, for example, you have 2 carbon, you have a carbon bonded to 3, next bonded to the next carbon to 3. You have 3, you have carbon CH3 group, then the next carbon has 2 hydrogen, the next one has 3 hydrogen. So that is what we call a molecular structure. Now, for ease in representation, sometimes we use what we call line structures or skeletal structures. In skeletal structures, for example, I have used only one to represent heptane with the most number of carbons here. Each point represents a carbon, and you calculate the number of carbons by calculating the points starting from the terminal point. So, for example, this one you have 1, 2, 3, 4, 5, 6, 7, and that each of those points represents a carbon atom. So the rest, if not given, then should represent hydrogen atom. That is what we call a skeletal representation of alkanes. Now, we start with nomenclature. Now, going back, we have named the alkanes that I have given here. So how are the names in alkanes given? Now, naming of alkanes or naming of compounds is what we call nomenclature. Now, in naming of alkanes, the names of alkanes generally have 2 parts. A prefix, that is the front part. For example, in methane, the prefix is meth. Then there is a common part you notice in all of them, that is A and E, and that is what we call the suffix. Now, there is the general, before the naming systems were developed, there are those general names that are used, and those are referred to as common names. But the most accepted and most uniform way of naming organic compounds is what is referred to as the IUPAC system of naming, where we have specific formula. And in naming of straight chain alkanes, the prefix for those with carbon 1 is meth, those with 2 carbons is eth, those with 3 carbons is prop, and those with 4 carbons is but. So that a carbon molecule, an alkane molecule with 1 carbon only is referred to as methane. If it has 2, it is ethane. We add eth to N. If it has 3, then you have propane. If it has 4, it is but and N, butane. Now, from carbon number 5, the general way of getting the prefix, because you notice that the prefix is the one that is changing. The general way of getting the prefix is from the Greek formula of depicting the sum number of sides in a polygon. So if you have 5-sided polygon, you use pent as a representation, 6 hex, 7 hept, 8 oct, etc. So if a straight chain alkane has 5 carbons, which then we shall call it pentane. If it has 6, hexane. If it has 7, we shall call it heptane. If it has 8, we shall call it octane. So the general nomenclature of straight-chain alkanes is not difficult, so long as you are able to depict the prefix from the Greek naming system. Now, when it comes to the nomenclature of branched alkanes, then there are certain other considerations. So ignoring the old system of naming, the common names, we go to the systematic or the IUPAC system, and there are rules that guide the naming. One is that you have to find the longest continuous chain of carbon atoms and use it the same way we have used in depicting the prefix. For example, if we have this molecule, you see there is a side group. So we have to ignore the side group and count the longest chain, which is 1, 2, 3, 4, 5, 6. So in that case, this is a hexane, but it has a side group. And the side group has 1 carbon. So when we are naming the side group, if it is a carbon side group, if it has 1 carbon, it will have 3 hydrogens, meaning that it is 1 less to become an alkane. And we use the same prefix as we use in alkanes, but instead of using the suffix N, we use the suffix YL. So in that case, if it has, the side group has only 1 carbon, it becomes methyl. If it has 2 carbons, it becomes ethyl. If it has 3 carbons, then it should become propyl. In that case, our side group here is a methyl group because it has only 1 carbon. So in that case, this we have, when we are naming the alkane, we have to indicate the position of the side group. And in this case, it is in position 2. So this molecule will be referred to as 2-methylhexane. Now, consider that we have counted from the nearest terminal carbon. If we had counted from the other side, then it would have been at position 5. So we have to count, even if the methyl group was here, it will still be 2-methylhexane because we have to count from the nearest terminal. So that is one thing to note. So another example is where we have this methyl group here. This counting from the nearest terminal, it is 1, 2 in position 3. So this becomes 3-methyl, and because they are, this should be 1, 2, 3, 4, 5, 6. So it should be, this should be 3-methylhexane, not heptane. So that is how you name the basic nomenclature. And note, this is telling you that you have to count from the nearest terminal. This one, if you count from here, would be 6, 7 dimethylhexane. Now, notice di. If you have 2 similar groups, we use the prefix di to show that those are 2 similar groups. And we have to indicate their position. So we are indicating that we have a methyl group in position 2 and a methyl group in position 3. And the positions are separated by a comma, while the name and the positions is separated by a hyphen. So this becomes 2, 3 hyphen dimethylhexane, and not 6, 7, because we have to count from the nearest terminal. Now, we can have a situation where we have different side groups that are joined to the hydrocarbon. Now, we have to name the side groups. For example, this with 1, 2 carbons is an ethyl group. Looking at now using the skeletal structure, this one is a methyl group, this is a methyl group, this is an ethyl group. Now, when we are giving preference, we use the alphabetical order in preferencing side group. So ethyl with an E comes before methyl with an M as the first alphabetical letter. So in that case, in naming this, First of all, we have to count the wrongest thing. So this is not a methyl because it's part of the wrongest thing. So we have 3 methyl groups and 1 ethyl group. So we have a total of 9 carbons. Each position numbered is a carbon. So this is a nonane. Now, this becomes counting in a manner. When you are counting to give the numbers, the counting should be in a manner that gives the smallest sum. So the smallest sum would be where we count from this side. So it is 3 with a methyl, 4 with 2 methyl groups, and position 7 with a methyl group. So it is a trimethyl and an ethyl. We give the preference to ethyl because E comes before M. So this one becomes 3 ethyl, 4, we use a hyphen 4, 7, hyphen trimethyl nonane. So that is one thing to note, that we are using the preference of alphabetical order. Apart from the preference of alphabetical order, you note that we are saying where you have more than one group, one group occurring more than once, we are using the prefixes di, tri, etc. Now, those preferences are not considered in alphabetical order. Even if we had a dimethyl, in this case, I use this example. If we had only 2 methyl groups, it would have been a di, and D comes before E. But however, it would still have been 3 ethyl, whatever, then dimethyl, because di in this case would not be considered in preferences. Rule number 4 is that the parent alkane is the last part of the name that we have seen, that the parent which we are considering as the main molecule becomes last part of the name. We are preferencing the side groups when we are giving consideration. For example, here we have a molecule which is 1, 2, 3, 4, 5, 6, 7, and it has 3 side groups, an NO2 group and fluorine. An NO2 group is a nitro group. A fluorine is referred to as a fluoro. And this one is a methyl group. So which one would be a preference? I will just use that example. Now, F and N. F comes before N, but M comes before N. So in this case, we shall start with fluoro. But in numbering, we shall start in a manner that gives the lowest sum. So 2, 3, 4 is the lowest sum of numbers you can get. So the methyl group is position 2, but the fluoro group is in position 4, but it will be named first. So this one becomes 4 fluoro, 2 methyl, 3 nitroheptane. So you see, the order of naming is not as per their numbers, but rather the alphabetical order of names. You can look at another example. Let's look at a molecule like this one, a complex one. Now, when you are giving the side groups, or when you are giving the molecule, the name of a molecule, you consider the molecule or the molecule with the highest number of side groups. So, which molecule would have the highest number of side groups? If we consider 1, 2, 3, 4, 5, 6, 7, 8, 9, then we have 2 side groups. But those are not the highest. If we count from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, still we have 9 as the wrongest thing, but with more side groups. So this is the best count. And in that case, we shall have a propyl group here. We shall have 2 methyl groups, and we shall have a group here, a propyl group joined to a methyl. So this one becomes, the methyl is position 2 of the propyl group. So it is a 2-methyl propyl. And so in this naming, we shall name by considering the methyl as the first group. Then prop comes before, after M. So this one becomes 3,3 dimethyl 5. For this group, this group is blanched, is a side group which is blanched itself. It is a propyl group, a 3-carbon group with a methyl group in position 2. So we call it 2-methyl propyl 4-propyl nonane. So that is an example. So what you should consider, in this molecule, we could have had 2 molecules with 9 carbons, but we chose the one that gives you the highest number of side groups. Then we go to sources of alkanes. Petroleum is petrochemicals are one source of alkanes. In fact, they produce the highest number of alkanes, and most alkanes for industrial purposes are produced from oil refinery through fractionation, so that you get the different types of alkanes. We can also get from biological synthesis, that is, biological materials can undergo anaerobic oxidation. If they go to aerobic oxidation, usually they produce carbon dioxide and other simpler molecules, but through anaerobic oxidation, that is where we end up with alkanes. Now, looking at the physical properties of alkanes, is that alkanes generally, if I was to say, is that alkanes generally have lower melting and boiling points in consideration with inorganic molecules. And this is because the intermolecular, although we've seen that the carbon atom bonding is generally a covalent bond, but the carbon, the molecule, intermolecular bonds in alkanes is based on weak van der Waals forces. So meaning that the intermolecular bonds in alkanes are usually weak, and in that case, alkanes generally have lower melting and boiling points compared to other, to inorganic molecules. And carbon 1 to carbon 4. Molecules with carbon 1 to carbon 4 are gases at room temperature. Carbon 5 to carbon 17 are liquids. Those are usually what consists of gasoline, diesel, etc. While carbon 18 onwards are generally solids and semi-solids. You can have things like waxes, you can have tar, which is for road construction. Now, so what you notice is that when it comes to physical properties in terms of melting and boiling points, the melting and boiling points of alkanes increase with increasing molecular size. And this is because bonding in alkanes or in hydrocarbons generally depends on molecular size. The stronger, the bigger the molecular size, the stronger the van der Waals forces. Solubility, now because of lack of polarity, and the lack of polarity can explain the low melting and boiling point. Again, the lack of polarity means that alkanes generally are insoluble in polar solvents, such as the best example being water, but are soluble in nonpolar solvents, such as benzene, ether, chloroform, etc. Another thing that determines the melting and boiling point in alkanes is that when you have symmetrical alkanes, and symmetrical alkanes usually have even number of carbons, the packing generally determines the strength of van der Waals forces. When you have alkanes with even number of carbons, then what happens is that there is better packing and stronger van der Waals forces. So generally, we can say that even numbered alkanes have relatively higher melting and boiling points than their odd numbered, which are less symmetrical. Again, branching in alkanes causes poor packing, and this leads to lowering of melting and boiling point. So you can say that, for example, if you have hexane, linear hexane, then you have, say, 2,3-methylbutane, which has the same molecular formula. You'd expect 2,3-methylbutane to have lower melting and boiling point because of branching, which will cause poor packing. So generally, that is about physical properties. in terms of solubility and melting and boiling points. So we have covered that. Now, when it comes to chemical reactions, we can say that just like other organic compounds, and in fact, more than many other organic compounds, alkanes are highly inert. And that is why petrochemicals such as pentane, hexane, these are part of what forms gasoline, are very unreactive. And you can store substances or materials, elements like metals in petrochemicals because of the inert nature of alkanes. However, when it comes to reaction with oxygen, if you have petrol and oxygen, they will not react on their own. But if you introduce a spark, the reaction is spontaneous, and the result will be carbon dioxide and water. In case you don't have enough oxygen, then what we have is what we call incomplete combustion, and you can have a result being production of carbon monoxide and water, or even you can have incomplete combustion where you end up with formation of carbon, that is soot. That is why you see in odd regions producing dark color, that is generally soot. So oxygen can react. So we say that the reason why oxygen in the atmosphere will not react with alkanes without a spark is we say that we need activation energy to cause the reaction. And we say that alkanes are thermodynamically unstable to oxygen, but kinetically stable to oxygen. So halogenation is reaction with halogens. Halogens are group 7 elements. Generally, in the dark, alkanes will not react with halogens. But in the presence of sunlight, alkanes are able to react with halogens through what is referred to as free radical substitution reaction. That is, the halogens, which molecules, which usually exist as bimolecular, biatomic, chlorine, bromine, iodine, etc. Although bromine, you can ignore fluorine in this case because fluorine, being highly electronegative, will react spontaneously. But if you are considering chlorine, bromine, and iodine, they will only react with alkanes in the presence of sunlight. And that is one way of differentiating alkanes with unsaturated hydrocarbons like alkenes and alkynes. And the reason why we need sunlight is that sunlight is able to break the biatomic molecules of halogens to their resulting radicals. That is, because the double bond, the bond that joins the atoms consists of 2 electrons. Each each atom goes with its own electron. And that radical formed is able to pluck hydrogen from the alkane, forming hydrohalogen or halogeno acid. Hydrohalogens like HCl, an acid, and then you leave a radical. In this case, an alkyl radical, in this case a methyl radical, which can then react with the next radical. Or rather, even if it does not react with the next radical, it can cause the breakdown of another molecule. And the reaction continues depending on the amount of halogen molecules that are present. And you can have all the hydrogens replaced. Or if you have very little of the halogens, only a few of the hydrogens will be replaced. Now, another type of reaction that alkanes undergo is what is referred to as pyrolysis, or what is otherwise commonly referred to as cracking. Cracking is where you break down long-chained alkanes into smaller alkanes. And this is important. For example, in oil refineries, usually you may find that you have long-chained alkanes in excess of what is required, you may need to break them to smaller alkanes which are of the nature of petrochemicals so that they can get to use. So breaking down of alkanes required high temperatures. That is what we call thermocracking, or it can be aided by catalyst, what we call catalytic cracking. So that is another reaction that alkanes involve themselves in. So, but we generally can say that alkanes are quite inert and are involved in very rare reactions. If we go backwards, in terms of oxidation, though we are showing that there is a possibility of branched alkanes to be oxidized, it is a very rare occurrence and it requires harsh circumstances. So generally we can say that alkanes are not easily oxidized by oxidizing agents, and apart from blanched, that reaction will not occur. And one way of differentiating between alkanes and alkenes is the lack of oxidation by oxidizing agents to alkanes. Now, lastly, we look at other types of alkanes, the cycloalkanes, very briefly. Cycloalkanes are the ones that where carbon joins in rings. So if, again, just like in normal alkanes, when you're naming cycloalkanes, you name them by counting the number of carbons. So if it has 3 carbons, it's a propane, but you add a prefix cyclo to indicate that it is cyclic. If it has 4, you add to butane cyclo, etc. Now, when if you have branched cycloalkanes, or if you have substituted cycloalkanes, usually you consider the first substitute as position 1. So, and you number them in a manner whether clockwise or anti-clockwise that gives you the lowest numbers. So then you have, we end up with looking at exercise questions. So one question, define the term cracking from the constitutional isomers of C7H16. Draw 2 structural formulas. You can even draw more and try to name them. When we mean structural formulas, is that you, so long as you have 7 carbons and 16 hydrogens, you can try to show the number of alkanes that you can form, whether cyclic or non-cyclic, and try to name them. Then you are given names of alkanes, and you are supposed to draw the structural formulas. Thank you. That is the end of lesson 2.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.